You were told these are three separate mountain ranges on three separate continents, with three separate names in three separate languages, belonging to three separate geological stories. They are not. There are mountains in North America. There are mountains in Norway and Scotland. There are mountains in Morocco and Algeria. Three different continents, three different countries, three different ranges with different names in different languages. And yet, they are the same mountains. 300 million years ago, they formed one continuous range nearly 6,000 miles long, longer than the modern Himalayas, taller than the modern Everest, stretching across the center of the supercontinent Pangaea, like a spine across the back of a giant animal. The Central Pangean Mountains, the most magnificent mountain range in the history of this planet. And today, only three fragments remain, on different continents, separated by thousands of miles of ocean. Today, I want to tell you the story of how that happened. Before we go any further, please subscribe to this channel. Your support is what makes this work possible, and I genuinely appreciate it. Thank you. Let's begin with a problem. If you are a geologist working in the 1950s and you are mapping the rocks of the southern Appalachian Mountains in Virginia or North Carolina, you keep finding something that doesn't make sense. The rocks are wrong. Not wrong in the sense of being unusual or exotic. Wrong in the sense of being somewhere they should not be. Ancient, metamorphic and igneous rocks, some of them 500 million years old, sitting on top of younger sedimentary rocks that they have no business sitting on top of. The geometry is impossible if you assume the rocks have always been where you find them. They appear to have traveled, moved, arrived from somewhere else entirely, and the direction they came from when you trace the structures carefully is east, from the ocean, which makes no sense at all, because there is nothing to the east but the Atlantic Ocean. And the Atlantic Ocean cannot be the source of ancient mountain-building rocks, unless, of course, the Atlantic Ocean didn't always exist. This is the intellectual knot that the Central Pangean Mountains helped untangle. Because when geologists in the 1960s and 70s began to seriously apply the new framework of plate tectonics to the Appalachians, they realized something extraordinary. The rocks that had traveled from the east, the exotic terrains, the displaced metamorphic belts, the thrust sheets that had been shoved westward over younger sedimentary sequences, these were not mysterious arrivals from a non-existent source. They were the roots of a mountain range that had formed when another continent had collided with North America. A continent that subsequently pulled away, taking with it the eastern half of what had once been a unified mountain belt, opening the Atlantic Ocean in the gap between. The Appalachians, in other words, are not simply mountains. They are the western remnant of a collision zone, the scar of an ancient continental suture. And the other side of that suture is now sitting in Europe, in the form of the Caledonian Mountains of Scotland, Norway, and Greenland, and in Africa, in the form of the Atlas Mountains of Morocco and Algeria. To understand how this happened, how one mountain range became three, separated by thousands of miles of ocean, you need to go back much further than the Appalachians. You need to go back to before Pangaea existed. You need to go back to when the continents were assembling, not breaking apart. 480 million years ago, the world looked nothing like it does today. The familiar shapes of the modern continents did not exist. In their place were a different set of continental fragments, arranged in a completely different configuration, separated by oceans that no longer exist and connected by land bridges that have since been destroyed. The largest landmass was Gondwana, a massive supercontinent comprising what would become South America, Africa, Antarctica, Australia, and India, sitting in the southern hemisphere. To the north were several smaller continents: Laurentia, which would become the core of North America; Baltica, which would become Scandinavia and Eastern Europe; and Avalonia, a smaller fragment that would become much of Western Europe and parts of the northeastern United States and Atlantic Canada. Between these landmasses lay two oceans: the Iapetus Ocean, sometimes called the Proto-Atlantic because it occupied roughly the same geographic space that the Atlantic Ocean later would, separated Laurentia from Baltica and Gondwana; and the Reich Ocean separated Avalonia and Baltica from Gondwana to the south. These were real, full-sized oceans, comparable in scale to the modern Atlantic or Pacific. The Iapetus, at its maximum, was probably at least as wide as the modern Atlantic, perhaps wider. It had mid-ocean ridges. It had deep ocean trenches. It had abyssal plains. It had, in other words, everything a proper ocean has. And then it began to close. The closing of the Iapetus Ocean is one of the most important geological events in the history of the Northern Hemisphere, and it happened in stages over roughly 150 million years, through a series of collisions that geologists call the Caledonian and Akkadian orogenies, mountain-building events that progressively assembled the pieces of what would become the Central Pangean Mountains. The first stage began roughly 480 million years ago, when subduction zones formed at the margins of the Iapetus Ocean and began consuming the oceanic crust. As the ocean floor was pulled down into the mantle, the ocean slowly shrank. Island arcs, chains of volcanoes similar to the modern Japan or the Philippines, formed above the subduction zones, rising from the ocean as the subducted oceanic crust released water into the overlying mantle and triggered volcanic eruptions. Some of these island arcs eventually collided with the margins of Laurentia, adding new material to the continent's edge and beginning the process of mountain building. The tectonic orogeny, which peaked roughly 450 to 440 million years ago, was the first of these collision events, a series of island arc collisions that built an early mountain range along what is now the eastern margin of North America. The rocks created by this event are preserved today in parts of the Appalachians, the metamorphic and volcanic rocks that geologists call the tectonic allochthon, sheets of rock that were thrust westward over the continental margin as the island arcs arrived. Picture what this looked like. The coastline of ancient Laurentia, running roughly where the modern Appalachians now stand, was not the gentle, passive margin we know today. It was an active subduction zone, with volcanoes erupting along the eastern coast, deep ocean trenches offshore, and periodically island arcs slamming into the margin from the east as the Iapetus Ocean shrank. With each collision, the mountains grew. With each addition of new material from the closing ocean, the continental margin thickened and rose. Then, approximately 400 million years ago, Baltica, the continental fragment that would become Scandinavia, Finland, and parts of Russia, closed the northern Iapetus and collided with Laurentia. This event, the Caledonian orogeny, was a full continent-continent collision, the most powerful type of mountain-building event that geology knows. When two continents collide, neither one can be subducted. Continental crust is too buoyant to sink into the mantle. Instead, the crust crumples and thickens. It piles up. It shortens horizontally and thickens vertically, building mountains in the same way a tablecloth piles up when you push its two ends toward each other across a smooth table. The Caledonian orogeny produced mountains on both sides of the collision. On the Laurentian side, the mountains are preserved today as the Northern Appalachians, in New England, in the Canadian Maritimes, in Newfoundland. On the Baltican side, they are preserved as the Caledonides, the mountains of Scotland, Norway, and Greenland. And when you match the rocks on either side of the modern North Atlantic, they fit with extraordinary precision. The same rock types, the same deformation structures, the same metamorphic grades, the same ages, all of it matching across 3,000 miles of ocean, the two halves of a mountain range that was torn apart 160 million years after it formed. This matching was one of the early triumphs of plate tectonics as an explanatory framework. In the 1960s, a Canadian geologist named J. Tuzo Wilson, one of the architects of plate tectonic theory, proposed what is now called the Wilson cycle, the idea that ocean basins open and close repeatedly over geological time, assembling and dispersing supercontinents in a rhythm with a period of roughly 500 million years. The Iapetus Ocean, Wilson argued, had been a predecessor of the Atlantic. It had opened, then closed as the continents assembled Pangaea. And then a new Atlantic had opened in almost the same place as the old Iapetus had been. The modern Atlantic is not the first ocean in this location. It is the second. The first one closed, built mountains in the process, and then a new one opened, tearing those mountains apart. This is a concept of almost vertiginous geological depth. The Atlantic Ocean is not ancient. It is young, barely 180 million years old, and it formed in approximately the same space where an older ocean had previously closed, leaving the joined continents behind, which then took 300 million years to reassemble. Enough internal stress to rift apart again. The rocks of the Appalachians and the Caledonides are, in a very real sense, the geological memory of the first ocean. They are the scar tissue of a world that no longer exists, the suture line of a collision that happened before the current configuration of continents was even imagined. But the collision that created the Central Pangean Mountains at their grandest was not the Caledonian. That came later. Beginning roughly 380 million years ago, a new phase of ocean closing and continental collision began in earnest. The event geologists call the Acadian orogeny in North America and the Variscan orogeny in Europe. This was the main event. the collision that built the mountains to their maximum height. And it involved a continent arriving from the south, Gondwana. By 350 million years ago, the Rhaetic Ocean, the ocean separating Baltica and Laurentia from Gondwana, was closing. The mechanisms were the same as before: subduction consuming the oceanic crust, island arcs forming and colliding with the continental margins, the ocean progressively shrinking. But the scale of what was coming was larger. Gondwana was not a small continental fragment. It was a supercontinent, a vast, massive landmass that carried with it the weight of enormous geological momentum. When Gondwana began to collide with the assembled Laurentia-Baltica block, the result was mountain building of a scale that the Earth has rarely seen. The Akkadian Variscan orogeny peaked roughly 320 to 300 million years ago. At its maximum, the mountains it produced were extraordinary by any standard. Geologists estimate the height of the Central Pangean Mountains by working backward from the volumes of sediment they shed, the enormous quantities of erosional debris that washed off the mountains and was deposited in the foreland basins to the west and south. These sedimentary sequences are thick, extraordinarily thick. In some places, the Devonian and Carboniferous clastic wedges, the river deltas and alluvial fans that formed at the foot of the mountains, are tens of thousands of feet deep, recording the relentless erosion of a mountain range that was shedding material as fast as tectonics could build it up. When geologists calculate the crustal thickness required to produce that volume of erosional sediment, the numbers are humbling. The Central Pangean Mountains at their maximum likely had peaks reaching elevations of at least 30,000 feet, comparable to or exceeding the modern Himalayas. Some estimates suggest they may have been even higher, perhaps approaching 40,000 feet in their core zones, where the collision was most intense and crustal thickening greatest. For comparison, Mount Everest today stands at 29,032 feet. The highest point in the Appalachians today, Mount Mitchell in North Carolina, stands at 6,684 feet. What happened to the missing 23,000 feet? Erosion. Time. 350 million years of it. The story of the Appalachians is, in large part, the story of erosion. From the moment the mountains stopped growing, from the moment the collision ceased and the tectonic engine that was building them switched off, the forces of erosion began their patient, relentless work. Rain fell, rivers formed, glaciers came and went many times. Chemical weathering slowly dissolved the minerals in the rock. Physical weathering broke the rock into fragments. Every fragment that washed downstream was a millimeter, or a micron, or a nanometer subtracted from the mountain's height. Over 350 million years, that adds up to something like 5 vertical miles of rock removed from the Appalachian surface. What you see when you look at the Appalachians today is not the mountains. It is the roots of the mountains. You are looking at rock that, when these peaks were at their maximum height, was buried perhaps 10 to 15 miles below the summit. The metamorphic rocks that form the cores of the Appalachian ranges, the gneisses and schists exposed in the Blue Ridge and the Reading Prong and the Green Mountains of Vermont, were formed at depths and temperatures that correspond to being buried under the equivalent of 10 to 15 miles of overlying rock. The overlying rock is gone, worn away by 350 million years of erosion. What remains is the deep interior of the mountain range, exhumed by that erosion and now sitting at the surface, waiting for geologists to read it. This process, the gradual removal of overlying rock, the slow exhumation of the deep crustal roots, is not unique to the Appalachians. It is what happens to every old mountain range. The Caledonides of Scotland and Norway are similarly exhumed. The Atlas Mountains of Morocco preserve a somewhat different erosional history, partly because of their position relative to the Sahara Desert, which is a more efficient preserver of rock than the humid temperate climates that attacked the Appalachians and Caledonides. But all three fragments of the Central Pangean Mountains show the same fundamental characteristic. They are the remnants of something much, much larger. They are archaeological sites, in a geological sense, places where the deep interior of an ancient world is exposed and readable at the surface. But let's step back from the erosion for a moment and think about what the Central Pangean Mountains meant for the world while they existed. Because the consequences of a mountain range of this scale are not limited to its immediate geography. They extend to the climate, the atmosphere, the evolution of life. The Carboniferous period, roughly 350 to 300 million years ago, was one of the most extraordinary intervals in Earth's history. It was the age of the great coal swamps, the vast forests of giant club mosses and tree ferns that would eventually become the coal seams of Pennsylvania, Virginia, Wales, and the Ruhr Valley. And those forests existed, in significant part, because of the Central Pangean Mountains. Here is how the connection works. Mountain ranges affect climate by intercepting moisture-laden winds, forcing air upward, cooling it, causing it to precipitate. The windward side of a mountain range receives abundant rainfall. The leeward side is in a rain shadow and is dry. The Central Pangean Mountains, running east-west across Pangaea near the equator, created an enormous belt of high rainfall on their flanks, a tropical and subtropical humid zone that extended across much of what is now the eastern United States and western Europe. This humid zone, combined with the warm Carboniferous temperatures and the equatorial position of the landmass, produced the conditions for the coal swamps. And the biological consequences of this were stranger and more spectacular than almost anything else in the history of life on land. Stand in a Carboniferous forest for a moment and try to see it clearly. Not the romanticized version, not a dim, steamy jungle with generic prehistoric plants. The real thing. The plants are wrong. They are wrong in the way that deeply alien things are wrong, recognizably plant-like, with stems and leaves and something that functions like bark, but scaled and proportioned in ways that violate every expectation formed by looking at modern forests. Lepidodendron, the giant club moss, grows to heights of over 100 feet. Its trunk 2 to 6 feet in diameter. Its bark covered in a diamond-shaped pattern of leaf scars that gives it the texture of a scaled reptile rather than a tree. At the top, a sparse crown of grass-like leaves. It does not branch the way modern trees branch. It grows straight, almost unbranched, for most of its height, then forks a few times near the top. It looks less like a tree than like an enormous green column, slightly tapered, crowned with a tuft of foliage. Sigillaria stands beside it, another giant club moss, similar in form but slightly different in its bark pattern and crown architecture. Between them, calamites, giant horsetails, also reaching heights of 60 to 90 feet, their hollow, jointed stems giving them the appearance of enormous bamboo. And everywhere, covering the swampy ground and climbing the trunks, cordites, primitive seed plants with long strap-like leaves, the ancestors of the conifers that would dominate the Mesozoic. The understory is dense with tree ferns, Psaroneus medulosa, their fronds enormous, their trunks supported by a mantle of adventitious roots that spreads outward at the base like a skirt. This forest is not quiet. It is producing oxygen, enormous quantities of oxygen, through the photosynthesis of billions of plants in a warm, wet, CO2-rich atmosphere with strong tropical sunlight. The oxygen is not being fully consumed. The dead plant material in the swampy conditions is being buried rather than decomposed. The anaerobic conditions of the waterlogged forest floor prevent the bacteria and fungi that would normally break down dead organic matter from doing their work efficiently. The carbon is being locked away. The oxygen is accumulating. By roughly 300 million years ago, the oxygen content of the atmosphere had risen to somewhere between 27 and 35% compared to today's 21%. And this change in atmospheric chemistry opened a biological door that had never been opened before and has not been opened since. Insects breathe by diffusion. They have no lungs, no respiratory muscles, no active pumping mechanism to move air in and out of their bodies. Instead, oxygen diffuses passively through a network of tubes called tracheae that open at the surface of the body through small holes called spiracles, branching progressively finer until they reach individual cells. This system works well for small insects. It works less well for large ones because the diffusion distance, the distance oxygen must travel from the spiracle to the innermost cells, increases with body size. And diffusion becomes slower and less efficient over longer distances. In a normal atmosphere with 21% oxygen, this constraint limits insect body size. The largest modern insects, the Goliath beetle, the Atlas moth, the giant wheater of New Zealand, approach the functional limit of what tracheal diffusion can supply. They cannot get significantly larger without their innermost cells running out of oxygen. But in an atmosphere with 30% or more oxygen, the higher partial pressure of oxygen drives diffusion faster and further. The constraint relaxes. The size limit shifts upward. And the carboniferous insects, living in an atmosphere richer in oxygen than any the Earth has seen before or since, grew to sizes that would be impossible in any other period of Earth's history. Meganeura monyi, the giant griffinfly, a member of the order Meganisoptera, had a wingspan of roughly 28 inches, nearly 2.5 feet from wingtip to wingtip. It was not technically a dragonfly. Its relationship to modern dragonflies is roughly analogous to the relationship between an alligator and a modern lizard, sharing a distant ancestor, but diverged for 350 million years. But it looked like a dragonfly scaled up to the size of a hawk. Its compound eyes were enormous, providing near panoramic vision. Its legs were armed with spines for snatching prey in flight. It was an aerial predator at a scale the modern world does not contain. Arthropleura armata was stranger still and larger. A relative of modern millipedes and centipedes, an arthropod segmented with many pairs of legs, Arthropleura reached lengths of up to 7.5 feet and widths of nearly 20 inches. It was the largest land invertebrate in Earth's history. Its trackways, the fossilized footprint trails it left in Carboniferous sediments, have been found in Scotland, in Germany, in North America. Parallel rows of small impressions, widely spaced, indicating a body moving with surprising speed across the wet forest floor. What it ate remains debated. The structure of its mouthparts suggests it may have been an herbivore, feeding on the rich plant material of the coal swamp forest, though some researchers have suggested it may have been omnivorous. What is not debated is its scale. 7.5 feet of arthropod, moving through a forest of 100-foot club mosses in an atmosphere thick with oxygen, at the foot of mountains that were still rising to the south. And the amphibians. The Carboniferous was the golden age of early tetrapods, the first vertebrates to colonize the land, and several lineages of Carboniferous amphibians grew to sizes that dwarf any modern amphibian. Eriops, a robust, crocodile-like amphibian, reached lengths of 6 feet. Proterogyrinus was similarly large. And Anthracosaurus, an apex predator of the Carboniferous swamps, may have reached lengths of 10 feet or more. A predator at the top of the food chain in the coal swamp ecosystem, moving between the water and the land with the easy confidence of an animal with no rivals. These giants were made possible by the oxygen. The oxygen was made possible by the burial of organic carbon. The burial of organic carbon was made possible by the swampy conditions at the foot of the growing mountains. And the swampy conditions were made possible by the climate that the Central Pangean Mountains created. The orographic rainfall on their flanks, the warm, humid belt they sustained. Take away the mountains, and the oxygen-rich atmosphere does not develop. Take away the oxygen, and the giant insects and giant amphibians do not exist. The Central Pangean Mountains did not just shape the landscape, they shaped the bodies of the animals that lived in their shadow. But the oxygen story has a dark side. In an atmosphere with 30% oxygen, combustion is dramatically easier. Fire ignites more readily, burns hotter, spreads faster. The evidence for extensive wildfires in Carboniferous deposits is abundant. Fossil charcoal, called fusain, is found throughout Carboniferous coal seams, showing that the coal swamp forests burned repeatedly and extensively. Lightning strike fires, spreading through a forest in an oxygen-rich atmosphere, would have been far more devastating than any modern wildfire. The coal swamp ecosystem was not a stable paradise. It was a world of extraordinary biological productivity, interspersed with catastrophic, oxygen-fueled fires that periodically consumed enormous areas of forest, releasing stored carbon back into the atmosphere and temporarily checking the oxygen buildup. The planet was regulating itself, clumsily but effectively, building up oxygen in the biomass and soil of the coal swamps, periodically releasing it through fire, the carbon cycling between the living forest, the buried coal, and the burning canopy in a rough equilibrium that kept the system within survivable bounds. This is not a designed system. It is an emergent property of the chemistry, the same kind of self-regulating feedback that operates in the carbon silicate cycle, but operating on a shorter timescale through the medium of fire rather than weathering. And then the climate began to change. By the end of the Carboniferous and into the Permian, the CO2 drawdown caused by the Central Pangean Mountains silicate weathering, combined with the burial of carbon in the coal swamps, had cooled the planet to the point where the extensive glaciation of Gondwana was well underway. The coal swamp forests, which depended on warm, humid tropical conditions, began to contract. The giant insects and amphibians that had thrived in the oxygen-rich Carboniferous atmosphere found their habitats shrinking. By the early Permian, the great coal forests were gone from most of their range, replaced by drier, cooler vegetation dominated by seed plants, which could survive the seasonal droughts that the cooling climate was now imposing. The biological legacy of the Central Pangean Mountains, the giant insects, the coal forests, the oxygen spike, the ice age, played out over roughly 100 million years, from the mountain range's maximum growth in the late Devonian to the final decline of the coal swamp ecosystem in the early Permian. 100 million years of biological consequence, all traceable back to the same tectonic event. The collision of Gondwana with the assembled Laurentia Baltica block, the rise of the greatest mountain range in Earth's history, and the slow, relentless erosion that filled the foreland basins with sediment and buried the forests in the swamps that would become coal. But the mountains affected the atmosphere in an even more direct way. As they rose, they exposed enormous areas of fresh silicate rock to chemical weathering. Silicate weathering consumes carbon dioxide from the atmosphere, the same mechanism we discussed in the context of the Himalayas, but operating on an even larger scale. As the Central Pangean Mountains grew through the Devonian and into the Carboniferous, the rate of silicate weathering increased dramatically, pulling carbon dioxide out of the atmosphere at rates that significantly exceeded volcanic inputs. And the cooling of the climate by the CO2 drawdown had another consequence. By the late Carboniferous, roughly 300 million years ago, glaciers had begun to form on Gondwana, which at this time was positioned over the South Pole. What followed was one of the most severe ice ages in Earth's history, the Karoo Ice Age, or the Late Paleozoic Ice Age, which lasted roughly 100 million years and repeatedly glaciated the southern portion of Pangaea. The coal deposits of India, South Africa, and South America record this glacial period in their interbedded sequences of coals and glacial deposits. The alternation of warm, swampy intervals with cold glacial ones, driven by the same kind of orbital forcing that drives the Quaternary ice ages. All of this, the coal swamps, the giant insects, the Gondwana glaciation, connected, directly or indirectly, to the mountains that were rising in the center of Pangaea. Now, the mountains had been built. Pangaea was assembled. By roughly 300 million years ago, the world consisted of one supercontinent, Pangaea, surrounded by one super-ocean, Panthalassa, and running across the waste of Pangaea from what is now Morocco in the west to what would eventually become Afghanistan in the east. The Central Pangean Mountains formed the backbone of the world, a continuous, unbroken chain of peaks, with the Appalachian portion in the west, the Variscan belt through what would become Europe in the center, and the continuation into North Africa in the south. For roughly 50 million years, this configuration persisted. Pangaea was not static. Internal rifts were forming and failing, the edges were being eroded, the climate was changing, but the basic structure held. One continent, one mountain range at its center. And then, roughly 250 million years ago, everything changed. The largest mass extinction in Earth's history, the end Permian extinction, killed roughly 90% of all marine species and 70% of terrestrial vertebrates. The cause was the Siberian Traps volcanism, the eruption of roughly 3 million cubic miles of lava in what is now Siberia over a period of perhaps 1 million years, releasing enough CO2 and sulfur dioxide to collapse the carbon cycle, acidify the oceans, and trigger a runaway greenhouse warming that pushed surface temperatures to perhaps 15 or 20 degrees Fahrenheit above today's levels. The end Permian extinction did not directly cause the breakup of Pangaea, but it is the temporal marker that sits just before it. Within roughly 50 million years of the extinction, by about 200 million years ago, in the early Triassic and Jurassic, the rifting of Pangaea had begun in earnest. The first rift to develop within Pangaea ran through the Central Pangean Mountains themselves, not around them, through them. The same mantle heat that had helped build the mountains, the residual thermal anomaly beneath the thickened crust of the collision zone, now became the engine of their destruction. For the creatures living on Pangaea at the moment the rifting began, the experience of continental breakup was not dramatic in any individual lifetime. No animal felt the continent split. No forest was instantaneously divided. The process was too slow, measured in millimeters per year, in earthquakes spaced decades apart, in volcanic eruptions that might occur once every few thousand years in any given location. But over millions of years, the cumulative effect on climate, on geography, on the distribution of habitats and the connectivity of populations was profound. The Triassic period, the interval that began roughly 252 million years ago, in the immediate aftermath of the end Permian extinction, and lasted until roughly 201 million years ago, was the age of Pangaea's slow dissolution. And it was also, not coincidentally, the age in which the vertebrate world was rebuilt from the ruins of the greatest mass extinction in Earth's history. The end Permian extinction had left the terrestrial ecosystems of Pangaea devastated. 70% of terrestrial vertebrate species had been eliminated. The great synapsids, the mammal-like reptiles, The dominant large vertebrates of the Permian were largely gone, reduced to a handful of survivor lineages that would slowly diversify into the mammals of the Mesozoic. The ecological vacuum they left was enormous. And into that vacuum, during the Triassic, moved the archosaurs, the group of reptiles that would give rise to both the crocodilians and the dinosaurs. The early Triassic landscape of Pangaea was strange by any standard. The supercontinent stretched from pole to pole, a vast single landmass with an interior that was far from any ocean, subject to extreme continental climate, baking hot summers, cold winters, with rainfall concentrated near the coasts and the interior of Pangaea, a near desert of extraordinary aridity. The Pangean megamonsoon, driven by the enormous thermal contrast between the heated continent and the surrounding Panthalassa Ocean, produced intense seasonal rainfall along the coasts, but the continental interior received almost none. This extreme climate was shaped in part by the remnants of the Central Pangean Mountains. The old mountain belt, though heavily eroded by the Triassic, still had enough topographic expression to influence atmospheric circulation, to deflect winds, to create rain shadows and precipitation belts. The Triassic red beds, the distinctive red sandstones and siltstones that fill the Newark, Gettysburg, and other rift basins of the eastern United States, record an arid to semi-arid climate, the red color coming from iron oxide in sediments deposited in oxidizing, seasonally dry conditions. Dinosaur footprints, preserved in these red beds, tell us that animals were present, but the sedimentology tells us they were living in a landscape not unlike parts of the modern American Southwest. In the late Triassic, as the rifting accelerated and the Central Atlantic magmatic province erupted its flood basalts along the developing rift zone, the climate changed again. The camp eruptions released enormous quantities of CO2 into the atmosphere. Estimates suggest the equivalent of several thousand gigatons of carbon over a relatively short period, warming the climate, acidifying the oceans, and contributing to the end Triassic mass extinction at roughly 201 million years ago. The end Triassic extinction was not as severe as the end Permian, but it was still catastrophic, eliminating perhaps a third of all marine genera and significant numbers of terrestrial vertebrates, including the large cruratarsal archosaurs that had dominated Triassic terrestrial ecosystems. And what survived the end Triassic extinction and subsequently diversified into the dominant terrestrial vertebrates of the Jurassic and Cretaceous? The dinosaurs. The very eruptions that accompanied the final breakup of Pangaea and the destruction of the Central Pangean mountain range, the camp flood basalts, may have been responsible for eliminating the ecological competition that allowed dinosaurs to achieve their subsequent dominance. The breakup of the mountain range and the rise of the dinosaurs are, in this reading, not separate stories. They are the same story, told from different perspectives. As the Jurassic progressed and the Central Atlantic widened, the biological consequences of continental separation became increasingly apparent. Populations that had been connected across Pangaea, sharing genes, exchanging individuals, part of single broad species ranges, found themselves progressively isolated on separate continental fragments. The terrestrial faunas of North America, Europe, South America, and Africa, which had been broadly similar in the Triassic, began to diverge as the oceans between them widened and dispersal became impossible. By the late Jurassic, the dinosaur faunas of North America and Africa showed significant differences, reflecting tens of millions of years of evolutionary divergence in isolation. But the most dramatic biogeographic consequence of Pangea's breakup was not the divergence of the dinosaurs. It was the isolation of the southern continents. Gondwana, which had been the southern portion of Pangaea, from the northern continents, and the subsequent independent evolution of their faunas. The monotremes and marsupials of Australia, the unique mammals of South America before the Great American Interchange, the extraordinary endemic flora and fauna of Madagascar. All of these are biological legacies of the rifting of Pangaea, of the opening of ocean barriers that prevented gene flow and allowed evolutionary divergence to proceed unchecked for tens and hundreds of millions of years. And the mountains of the Central Pangean Belt, now on their separate continents, now separated by widening oceans, provided the high-altitude refugia, the orographic rainfall belts, the topographic diversity that sheltered and maintained biological diversity through the climatic upheavals of the Mesozoic. The Appalachians, even in their eroded, reduced state, maintained a north-south corridor of forested highland that would later become critically important as a refugium during the Quaternary Ice Ages, when glaciers covered the northern part of the range and species retreated southward along the mountain spine, surviving in the unglaciated southern Appalachians and later expanding northward as the ice retreated. The Central Pangean Mountains, or rather their 3 eroded fragments, have been shaping the distribution of life in the Northern Hemisphere for 300 million years. Not as the giants they once were, but as the persistent topographic features they remain, providing habitat structure, influencing local climate, maintaining the corridors and barriers that have guided the evolution and migration of countless species, from the Carboniferous to the present day. This is one of the most important and underappreciated principles in geology. Thick crust is gravitationally unstable. When a continent-continent collision thickens the crust to twice its normal depth, pushing crustal material down into the mantle as a deep root while building mountains above, the thickened crust creates a gravitational potential energy that wants to be released. The rock is too thick. It is pressing down on the hot mantle below, and the mantle is hot enough to flow. Over tens of millions of years, the deep crustal root slowly thins, flowing outward laterally as the buoyant lower crust spreads under its own weight. This process, called gravitational collapse, causes the mountains to sink even without erosion. It is why mountain ranges don't last forever, even if erosion stops. But in the case of the Central Pangean Mountains, the collapse was accelerated by something more dramatic. Beginning roughly 240 to 210 million years ago, a series of rifts began to propagate through the center of Pangaea. The most significant of these ran along the axis of the old mountain belt, The Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history, erupted along rift zones that cut directly through the Appalachian-Variscan Atlas system. The Central Atlantic Magmatic Province, the CAMP, produced enormous volumes of flood basalt lava, erupting from fissures that opened along the length of what would become the Central Atlantic margins. The lava flows are preserved today on 4 continents: in the Newark Basin of the eastern United States, in Morocco and Algeria, in Brazil, and in West Africa, all of them representing the volcanic activity that accompanied the rifting of Pangaea along the line of the old mountain belt. Their age is remarkably consistent across all 4 continents. Approximately 201 million years old, give or take a few million years. All of them erupted in the same brief geological instant as Pangaea began to tear apart. The rift that the camp accompanied was not a single clean break. It was a complex, braided system of grabens and half-grabens, fault-bounded basins that dropped down as the crust stretched and thinned. The modern Appalachian Highlands are flanked to the east by a series of these Triassic rift basins: the Newark Basin of New Jersey and Pennsylvania, the Gettysburg Basin, the Culpeper Basin of Virginia, elongated depressions that formed as the rift pulled the crust apart. These basins filled with red sediments, the distinctive red sandstones and siltstones of the Triassic, and with the lava flows of the camp. They are the geological record of the moment when North America began to separate from Africa. And the separation was precisely through the old suture zone, the zone where Africa and North America had been joined by the collision that built the mountains. The rift followed the line of least resistance, which was also the line of greatest weakness. The ancient suture, where the 2 continents had been welded together 300 million years before. Like a seam in a piece of cloth, the suture was the weakest point in the fabric of Pangaea. When the rift came, it ran along the seam. This is a pattern that plate tectonics has confirmed repeatedly. Rifts prefer to follow old sutures. The Wilson cycle works precisely because the old suture zones, the scars of previous collisions, are the places where the crust is most fractured, most altered, most weakened by the fluids and metamorphism that accompanied the original collision. When new rifting begins, it finds these old weak zones and exploits them. The Atlantic Ocean opened along the scar of the Iapetus Ocean collision. The Red Sea opened along the scar of an older Proterozoic collision zone. Old wounds are where new breaks happen, so the rift that destroyed the Central Pangean Mountains was exploiting the same suture that the mountains had created. The mountains were destroyed by their own weakness. The rifting progressed southward over the course of roughly 20 million years. By about 180 million years ago, the early Jurassic, the Central Atlantic was open. A narrow seaway, perhaps only a few hundred miles wide at first, separated North Africa from the eastern seaboard of North America. It was shallow, warm, restricted, more like the modern Red Sea than the modern Atlantic. But it was growing. The mid-Atlantic ridge had begun its slow work of spreading the seafloor, pushing the continents apart at a few centimeters per year. As the ocean widened, the Central Pangean Mountains became three separate mountain ranges on three separate continents. The Appalachians, the North American fragment, found themselves on the passive margin of a widening Atlantic. No more compression, no more collision, just erosion, patient and relentless. Working on a mountain range that was now tectonically dead, no longer being built up by new collisions, slowly being ground down to its roots. The Appalachians began their long decline. From the Himalayan scale range, they had been at their maximum, to the modest, rounded, heavily forested highlands they are today. But their rocks tell the story of what they once were. The metamorphic grades in the core of the Blue Ridge record pressures and temperatures that correspond to being buried under 40,000 feet of overlying rock. The foreland basin sediments of the Appalachian Plateau, the thick sequences of Devonian and Carboniferous clastic rocks that form the coalfields of Pennsylvania and West Virginia, record the erosional output of a mountain range of Himalayan proportions. Everything that makes the modern Appalachians seem modest and old. The rounded profiles, the forested slopes, the gentle gradients, is simply the mark of time, of 350 million years of patient erosion working on the remnant of something that was once extraordinary. The Caledonides, the European and Greenlandic fragment, had a somewhat different subsequent history. After the Central Atlantic opened and separated North America from Africa, the northern North Atlantic did not open immediately. Britain, Greenland, and Norway remained connected for tens of millions of years longer, part of the same landmass. The Caledonian Mountains of Scotland, Norway, and eastern Greenland continued to erode together, shedding sediment into the North Sea and the Norwegian Basin. Before the North Atlantic finally opened along the Greenland-Norway margin, roughly 55 to 60 million years ago. When it did, the Caledonian Mountains were divided again. The Scottish and Norwegian Caledonides on the European side, the East Greenlandic Caledonides on the American side. A mountain range divided twice by two successive ocean openings. The Atlas Mountains tell a third story. After Pangea's initial breakup separated North Africa from North America, the African plate did not simply drift passively. Africa continued to move northward, and in the Cenozoic, roughly 60 million years ago, Africa began to collide with Europe. This collision, the same one that produced the Alps, reactivated some of the old Variscan structures in northwestern Africa, recompressing and partially re-elevating the ancient roots of the Central Pangean Mountains in what would become Morocco and Algeria. The modern Atlas Mountains are therefore not simply a preserved remnant of the original Central Pangean range. They are a remnant that was partially rejuvenated, squeezed again, pushed up again, given new topographic expression by the Africa-Europe collision. When you stand in the high Atlas of Morocco and look at the peaks around you, you are looking at rocks that have been deformed twice. Once 300 million years ago, when they were part of the greatest mountain range in Earth's history, and once again in the last 60 million years, when Africa crashed into Europe and gave the old roots a new lease on topographic life. This complexity, the layered deformational history, the multiple episodes of mountain building and erosion and rejuvenation, is what makes the Atlas Mountains geologically richer, in some ways, than either the Appalachians or the Caledonides. In Morocco, a geologist can stand at an outcrop and read at least two separate mountain-building events in the same piece of rock. The older Variscan fabric, preserved in the metamorphic texture and mineral assemblage, and the younger Atlas compressional structures, which folded and faulted the already metamorphosed Variscan rocks into their present configuration. Now I want to take you to a specific place that illustrates the Central Pangean connection better than any diagram or map. In Newfoundland, Canada, there is a place called the Humber Arm on the western coast of the island, where the geology is extraordinary. Here, preserved in an almost complete section, are the rocks of the ancient Iapetus ocean floor, ophiolites, sequences of oceanic crust and mantle that were abducted, thrust onto the continent during the tectonic orogeny. These rocks, the Betts Cove ophiolite, the Bay of Islands ophiolite, are slices of ancient ocean floor, almost 500 million years old, now sitting on dry land in Newfoundland, thousands of miles from any active mid-ocean ridge. They are exact geological equivalents of ophiolites found in Scotland and Scandinavia. The same rocks, the same age, the same history on both sides of the modern North Atlantic. The Ballantrae ophiolite in Scotland, the Solund Stafjord ophiolite in Norway. All of them fragments of the same ancient Iapetus ocean floor, abducted onto the continental margins during the same collision events, now distributed across different countries and continents by the subsequent opening of the modern Atlantic. This is the geological detective work that makes plate tectonics so intellectually satisfying. You find a rock in Newfoundland, you find the same rock in Scotland, you find the same rock in Norway. The rocks are telling you something that geography denies. These places were once together. The ocean between them is an illusion of the present moment, a temporary feature of the current configuration of the Earth's surface, no more permanent than any other arrangement the plates have adopted over 4.5 billion years. The Iapetus Ocean closed, Pangaea assembled. The Central Pangean Mountains rose. Pangaea rifted. The Atlantic opened. And the three fragments of the mountains are now on three continents, eroding, waiting, their rocks still carrying the memory of everything that happened to them. Let me bring this story to a place that is, for most people, completely familiar, and show you how different it looks once you know what you are looking at. The Shenandoah Valley of Virginia, one of the most beautiful landscapes in the eastern United States. A broad, gently rolling agricultural valley, framed on the west by the ridge and valley province of the Appalachians, and on the east by the Blue Ridge Mountains. Every autumn, millions of people drive the Skyline Drive and the Blue Ridge Parkway to see the fall foliage. The valley is peaceful, pastoral, ancient-looking, in the way that all old landscapes look ancient. What you are actually looking at is the eroded core of a mountain range that was once higher than the Himalayas. The Blue Ridge Mountains, which form the eastern wall of the Shenandoah Valley, are made of rock that was metamorphosed at depths of roughly 8 to 12 miles below the surface of the original Central Pangean mountain range. The pressure and temperature conditions recorded in the minerals of the blue-ridged gneisses, the garnet-bearing, staurolite-bearing, kyanite-bearing metamorphic assemblages, correspond to pressures of around 8 to 12 kilobars and temperatures of around 500 to 600 degrees Celsius. These are the conditions you find at depths of 25 to 40 kilometers below the surface. That rock is now at the surface because everything above it, 25 to 40 kilometers of overlying rock, has been eroded away over the past 300 million years. 25 to 40 kilometers. 80,000 to 130,000 feet of rock, removed grain by grain, molecule by molecule, by rain and rivers and ice and chemical dissolution over 300 million years. And what remains is the deep interior of the mountain range, sitting at the surface, exposed for hikers and tourists and leaf peepers to walk across without giving it a second thought. The Ridge and Valley province to the west of the Blue Ridge tells a different part of the story. Here, the rocks are sedimentary, Paleozoic limestone, shale, and sandstone that were deposited in the foreland basin at the foot of the growing Central Pangean Mountains. These rocks were not buried deeply enough to be metamorphosed, but they were compressed and folded and thrust westward as the collision progressed, creating the characteristic corrugated topography of the ridge and valley. Parallel ridges of resistant sandstone and valleys eroded in softer limestone and shale, running northeast-southwest for hundreds of miles. A frozen record of the lateral compression that the Acadian and Alleghenian orogenies imposed on the margin of Laurentia. Drive west from the Blue Ridge into the Ridge and Valley, and you are driving away from the collision zone into the foreland, reading the story of the mountain's growth in reverse, from the metamorphic core, through the thrust sheets, into the folded sedimentary sequences, and eventually onto the flat Appalachian plateau where the deformation died out and the rocks lie nearly flat. The entire cross-section of a mountain belt spread out across the landscape of Virginia and West Virginia and Pennsylvania, readable by anyone who knows what to look for. Across the Atlantic, in Norway, the same cross-section exists. The Western Gneiss region of Western Norway, one of the most tectonically important terrains in Europe, records the same metamorphic pressures and temperatures as the Blue Ridge. The rocks of the Western Gneiss region were subducted to depths of more than 100 kilometers during the Caledonian collision, a rare example of ultra-high pressure metamorphism, where the pressure was sufficient to transform ordinary minerals like quartz and feldspar into their ultra-high pressure equivalents, minerals like coesite and even tiny microdiamonds, stable only at depths exceeding 100 kilometers. These ultra-high pressure rocks were then exhumed, brought back to the surface over tens of millions of years, and are now exposed in the cliff faces and fjord walls of Western Norway. When you stand at the edge of a Norwegian fjord and look at the ancient gneisses in the cliff wall, you are looking at rock that was once more than 60 miles underground. The fjord itself, carved by glaciers during the Quaternary ice ages, has cut through the exhumed root of the Caledonian Mountains, exposing the deep interior of the ancient range in a vertical section of breathtaking clarity. And here is the detail that I find most extraordinary about the Caledonian-Appalachian connection. The suture zone, the actual line where the ancient continents were welded together, is exposed on both sides of the modern Atlantic. In New England and the Canadian Maritimes, the Avalon Zone marks the boundary between rocks of North American origin and rocks that were originally part of the European margin of the Iapetus Ocean, carried across on the Avalonia microcontinent as it collided with Laurentia. In Britain and Scandinavia, the equivalent boundary, the Iapetus suture, runs roughly through the Scottish borders, from the Solway Firth in the west to Lindisfarne in the east, and continues through the Oslo Graben and into Scandinavia. Both suture zones represent the same geological event, the final closing of the Iapetus Ocean and the welding of the continents together, preserved on opposite sides of the ocean that subsequently opened in the same location. The Iapetus suture in Scotland and the Avalon-Gondwana suture in New England are the two halves of the same ancient wound, separated by the 3,000 miles of Atlantic Ocean that opened between them in the Jurassic. Now let me come to the Atlas Mountains, and to a detail that most accounts of the Central Pangean Mountains skip over, but which I think is essential to the full story. When the Central Atlantic Rift separated North America from Africa, beginning about 200 million years ago, the break did not follow the Central Pangean mountain chain perfectly. It ran through it. But the suture zone in northwestern Africa, the zone where the old Gondwanan margin had been welded to the Laurentian-Baltican block during the Akkadian-Variscan orogeny, was left on the African side of the new ocean, which means that the Atlas Mountains contain within them the record of both the original mountain-building collision and the subsequent rifting. In the Anti-Atlas range of southern Morocco, the oldest part of the Atlas system, and in some ways the most geologically fascinating, you can find rocks that carry the Variscan metamorphic signature, then Triassic red beds that were deposited in the rift basins as Pangaea pulled apart, then Jurassic and Cretaceous marine sediments laid down as the new Atlantic Ocean covered the rifted margin, and then Cenozoic compressional structures that squeezed all of this earlier history into the modern Atlas fold belt as Africa pushed northward into Europe. 4 separate geological events, all recorded in the same mountain range. Variscan collision, Triassic rifting, Atlantic opening, Cenozoic recompression. The Anti-Atlas is not just a remnant of the Central Pangean Mountains. It is a complete geological autobiography, a place where you can read 400 million years of plate tectonic history in a single afternoon of fieldwork. The oil and gas deposits of the Atlas region, significant hydrocarbon reserves in Algeria and Morocco, are a practical legacy of this complex history. The Triassic rift basins that formed as Pangaea pulled apart created natural traps for hydrocarbons, which migrated from organic-rich source rocks into the porous Triassic reservoir rocks and were sealed by the later compression of the Cenozoic orogeny. The petroleum geology of northwestern Africa is, in large part, a direct consequence of the rifting of Pangaea through the old Central Pangean mountain belt. It is worth pausing here to appreciate the extraordinary irony of this. The same process that destroyed the Central Pangean Mountains, the rifting of Pangaea, created the geological structures that now contain some of Africa's most economically significant hydrocarbon reserves. Destruction and creation, as usual in geology, are the same process. Let me take you now to one more specific place, a place that brings the story of the Central Pangean Mountains into the sharpest possible focus. In the heart of the Appalachian Mountains, in the coal fields of southwestern Virginia and southern West Virginia, the seams of bituminous coal that powered the Industrial Revolution of the eastern United States are the compressed, transformed remnants of the Carboniferous coal swamp forests that grew at the foot of the Central Pangean Mountains. The coal in these seams is essentially fossilized sunlight, organic carbon that was fixed from the atmosphere by Carboniferous plants, buried in the anaerobic swampy conditions of the Foreland Basin, compressed and chemically altered over 300 million years into the dense, energy-rich material that drove the steam engines of the 19th and 20th centuries. The Industrial Revolution, in a very real sense, was powered by the chemical energy that Carboniferous trees extracted from sunlight at the base of a mountain range that no longer exists as such. When a 19th century steam locomotive burned Appalachian coal, it was, in a roundabout way, burning the forests that grew in the shadow of mountains that stood 300 million years ago, and the natural gas that heats homes in Pennsylvania and West Virginia today. Much of it is Devonian and Carboniferous gas, stored in the reservoir rocks of the Appalachian Basin. Rocks that were deposited as the Central Pangean Mountains were rising and shedding sediment into the foreland. The entire energy infrastructure of the northeastern United States is built, quite literally, on the geological legacy of the Central Pangean Mountain building event. Now I want to bring all of these threads together and look at the Central Pangean Mountains not just as a geological feature, but as a concept. Because what this story really tells us is something about the nature of permanence and impermanence on a geological planet. We tend to think of mountains as the most permanent things on Earth. They are larger than cities, larger than civilizations, larger than anything human beings build. They have been there since before we existed and will be there long after we are gone. They are the archetype of permanence in human culture, immovable, eternal, beyond time. But the Central Pangean Mountains were not permanent. They rose, they stood, they eroded, they were torn apart and scattered across the globe. What remains of them is 3 modest ranges on 3 separate continents, each one an eroded remnant of something that was once almost incomprehensibly large. The mountains are not eternal. They are episodes, events in the ongoing story of plate tectonics, which operates on timescales that make even mountains seem ephemeral. The Appalachians will continue to erode. In another 100 million years, if no new tectonic event rejuvenates them, they will be lower than they are today, perhaps reduced to a broad, barely perceptible swell on the surface of the continent. Their rocks still there, but their topographic expression nearly gone. The Caledonides of Scotland and Norway will likewise continue to erode, their fjords deepening, their peaks lowering. The Atlas Mountains, if the Africa-Europe collision continues, may actually rise for a while longer. But eventually, when the collision ends and the compressional forces relax, they too will begin their long decline. And eventually, in a few 100 million years, when the Wilson cycle completes another turn and the Atlantic begins to close, and North America begins to drift back toward Europe, the Appalachians and the Caledonides may once again be brought together. The same rocks that were separated 200 million years ago may be reunited. A new ocean may close. A new collision may occur. And from the roots of the old Central Pangean Mountains, a new mountain range may rise. The planet does not waste material. It recycles it. The rocks of the Appalachians and the Caledonides have already been through at least 2 complete Wilson cycles. Assembled in the Caledonian collision, eroded and partially destroyed, then reassembled and further modified in the Acadian-Variscan collision. Before that, their constituent minerals were part of even older mountain ranges, built during the assembly of even older supercontinents whose names, Rodinia, Columbia, Nuna, are barely known outside the specialist literature. Every grain of sand on a Virginian beach, every pebble in a Norwegian riverbed carries within it the record of multiple previous existences, multiple previous cycles of mountain building and erosion, stretching back not just hundreds of millions, but billions of years. The geologist Jan Zalasiewicz has written beautifully about the concept of rock as a medium of memory, a physical record of past events that is imperfect, fragmentary, but persistent across timescales that dwarf human comprehension. The Central Pangean Mountains no longer exist as mountains, but they persist as memory. In the rocks of the Appalachians, in the gneisses of the Norwegian fjords, in the folded limestone of the Moroccan High Atlas, the memory is distributed across 3 continents, written in different rock types and different structural geometries, but readable to anyone who knows the language. And that readability, that persistence of geological memory across hundreds of millions of years of erosion, rifting, and oceanic spreading is, I think, one of the most profound things about geology as a discipline. The Earth forgets nothing. It may bury, distort, partially erase, scatter across continents, but it never fully destroys the record. The information is always there, waiting in the rock for someone to learn the language and read it. And the reading of this language, the progressive decipherment of what the rocks of the Appalachians and the Caledonides and the Atlas Mountains are actually saying, is one of the great intellectual achievements of 20th century science. It did not happen all at once. It happened through the accumulation of thousands of small observations made by hundreds of geologists working in different countries and different decades that only cohered into a single narrative when plate tectonics provided the framework to connect them. Consider the problem that faced a geologist working in the 1930s or 40s, before plate tectonics, looking at the Appalachians. The rocks made no sense in any static framework. The metamorphic grades were wrong, too high for rocks near the surface. The structural geometries were wrong. Thrust faults pushing rocks westward from a direction that had nothing in it but ocean. The igneous rocks were wrong. Ophiolites, fragments of ocean floor sitting in the middle of a continental mountain range with no plausible mechanism for their emplacement. The paleontology was wrong. The fossils in some Appalachian terrains matched the fossils in Europe, not the fossils in the rest of North America. Each of these anomalies was explained away individually through increasingly baroque local hypotheses that required special circumstances and ad hoc mechanisms. The thrust faults were explained by vertical forces, by some mysterious upwelling from below. The ophiolites were explained as unusual igneous intrusions. The mismatched fossils were explained by transoceanic dispersal of organisms across open water. The metamorphic grades were explained by unusual thermal conditions. Every anomaly had its own explanation, unconnected to every other anomaly, the explanations multiplying until the geological literature on the Appalachians was an almost impenetrable thicket of competing local theories. And then plate tectonics arrived, and all of the anomalies disappeared simultaneously. The thrust faults made sense because they were the product of a continental collision that had pushed rocks westward. The ophiolites made sense because they were fragments of the Iapetus ocean floor, abducted onto the continental margin during the collision. The mismatched fossils made sense because the terrains that contained them had originally been part of Europe or Gondwana, carried across the closing Iapetus Ocean and accreted to North America. The metamorphic grades made sense because the rocks had been buried under the enormous crustal pile of a Himalayan-scale mountain range and had only been exhumed by 350 million years of erosion. One framework, all anomalies resolved. This is what a correct scientific theory does. It does not just explain the phenomena it was designed to explain, it unexpectedly explains phenomena that were not originally considered. Plate tectonics was not developed to explain the Appalachians. It was developed from the evidence of the ocean floor, the magnetic anomaly stripes, the mid-ocean ridges, the age distribution of oceanic crust. But when it was applied to the Appalachians, it resolved problems that had been accumulating for 100 years of careful geological observation. The man who more than anyone else worked out the specific connection between the Appalachians and the Caledonides, who traced the individual rock units across the Atlantic and matched them on both sides, was a Canadian geologist named Harold Williams, working in Newfoundland and the Canadian Maritimes in the 1960s and 70s. Williams and his colleagues developed the concept of tectonostratigraphic zones, the idea that the Appalachian mountain belt could be divided into a series of parallel belts, each one representing a different piece of oceanic or continental crust that had been accreted to North America during the successive phases of the Iapetus Ocean's closure. The Humber Zone, the Dunnage Zone, the Gander Zone, the Avalon Zone, each one a terrain with its own geological history, welded to the others in sequence as the ocean closed. And when Williams and his colleagues matched these zones to their equivalents in the British and Scandinavian Caledonides, the correlation was compelling. The Humber Zone of western Newfoundland matched the Moyne Thrust Belt of northwestern Scotland, The Dunwich Zone ophiolites of Newfoundland matched the Ballantrae ophiolite of southwest Scotland and the Leka ophiolite of Norway. The Gander Zone of eastern Newfoundland matched the Dalradian supergroup of Scotland and Ireland. The Avalon Zone of southeastern Newfoundland, named after the Avalon Peninsula, matched the Avalonian terrains of southern Britain, including the rocks beneath London and much of southern England. Piece by piece, the two sides of the Atlantic were matched. The mountain range that had been torn apart 160 million years earlier was being intellectually reassembled in the 1960s and 70s using the tools of modern geology by scientists working on opposite sides of an ocean that their predecessors had assumed was eternal. The same exercise was repeated somewhat later for the Atlas Mountains connection. The Variscan orogeny of Western Europe, the mountain-building event that represented the final assembly of Pangaea in the late Carboniferous, was traced into northwestern Africa through the Hercynian belt of Morocco and Algeria. The rock units matching across the Strait of Gibraltar in the same way the Appalachian and Caledonian units matched across the North Atlantic. The Anti-Atlas of Morocco, with its ancient Precambrian basement and its Paleozoic sedimentary cover deformed by the Variscan orogeny, was shown to be the southern terminus of the same mountain belt that ran through Iberia, France, Germany, and into Poland and Bohemia. And at the other end of the chain, in Afghanistan and Pakistan and Iran, where the eastern continuation of the Variscan belt disappears beneath the younger sediments of the Tethyan realm, geologists are still working to trace the full extent of the Central Pangean Mountain system, still finding new connections, still matching rock units across modern political boundaries and ancient ocean basins. The work is not finished. Geology, like all sciences, is a process rather than a product. Every new geochronological date, every new structural analysis, every new isotopic fingerprint of a metamorphic rock adds a small increment of resolution to the picture. The Central Pangean Mountains are better understood today than they were in 2010. They will be better understood in 2040 than they are today. The language gets richer with every generation of geologists who learn to read it. What strikes me most about this process, about the progressive reconstruction of the Central Pangean Mountains from their scattered fragments, is what it says about the relationship between observation and understanding. The rocks have always been there. The Appalachians have been mapped and studied since the earliest days of American geology, since the surveys of the early 19th century. The Caledonides have been studied since before Darwin. The Atlas Mountains have been examined since the French geological surveys of the colonial period. The evidence for the connection was always in the rocks, in the matching metamorphic grades, the correlating fossil assemblages, the paired ophiolite sequences. But without the framework of plate tectonics, the evidence could not be assembled into a coherent story. This is, I think, a profound lesson about the nature of knowledge. Evidence does not speak for itself. It requires a framework, a theory, a model, a conceptual structure within which it can be interpreted. The rocks of the Appalachians were saying the same thing in 1920 that they are saying today. But in 1920, geologists did not have the ears to hear it. The discovery of plate tectonics did not change the rocks. It changed the listeners. And this should make us appropriately humble about what the rock is saying to us today that we cannot yet hear. There are anomalies in the geological record, features that resist explanation within the current framework, observations that require special pleading and ad hoc hypotheses. Some of these will eventually be explained within the current plate tectonic framework as more data accumulates and the models improve. The rocks are always ahead of the theory. The history of geology is the history of learning to read an ancient language, one word at a time, never quite sure whether you have understood correctly, always aware that the text is far longer and richer than anything you have yet deciphered. The Central Pangean Mountains left their message in 3 fragments on 3 continents. We are still reading it. Wegener saw the fit. The Appalachian geologists saw the displaced rocks. Tharp mapped the ridge. Marie Tharp could map the mid-Atlantic ridge, but the full implications of what she was mapping, that the ridge was the engine of continental separation, that it was the reason the Appalachians and the Caledonides were now on different continents, took years to fully work out. The story of the Central Pangean Mountains is, in part, a story about the progressive learning of a language written in rock over hundreds of millions of years that human beings have only begun to fluently read in the last 50 years. What I find most extraordinary about the Central Pangean Mountains is not their size, though they were extraordinary in size. It is not their age, though 350 million years is a number that defeats ordinary human intuition. It is the fact that they are still here, not as mountains, not as the range they once were, but as information, as geological memory, distributed across 3 continents, encoded in metamorphic textures and fold geometries and ophiolite sequences and coal seams, waiting for the next geologist to stand in front of an outcrop and ask the right question. The Appalachians are not humble mountains. They are not modest hills that happen to end up in the eastern United States. They are the roots of something that was once among the grandest features this planet has ever produced. And when you drive the Blue Ridge Parkway in October, with the leaves turning and the valleys spread out below you, and you think you are looking at scenery, you are actually looking at the deep interior of a mountain range that was once higher than Everest, formed when 2 continents collided 350 million years ago, and has been eroding ever since, patiently, grain by grain, toward the sea. That is not scenery. That is memory. The memory of a world that no longer exists, written in the oldest language on Earth.